Welcome to the Embedded System Design using ARM Cortex M4 series. I warmly welcome you to the session. Thank you for your time and thanks for coming today. Today is day 16 and today topic we are going to cover up what is interrupts. Okay, so we are going to cover up the difference between interrupts and polling and what is nested vector interrupt controller and what are the NVIC registers and what is EXTA, external interrupts, what are internal interrupts and what are external interrupts, and what is preemption and what is state changing, and finally how to write a program for an interrupt. Okay, so we'll be writing two programs today. One is the program for GPIO to generate interrupts using a GPIO using EXTI. The other is the UART interrupts. Okay, so whenever you receive a data, an interrupt is generated. I'm going to use the same code which we have used in the previous program. So whenever a data is received on the UART, we'll generate an interrupt and it goes for the interrupt service routine. Okay, so these are the two programs which we are going to cover up today. I hope you will have a great learning. Once you go through this program, I'm sure that you will be writing your own interrupt program. Okay, so I'll start with an announcement. The attendance link will be available at the end of the session. Minimum attendance required to get a free certificate is 25 days. You may get a waiver for 1 or 2 days. For internship candidates, no need to fill the attendance form. All you have to do is, after watching the video on the portal, just give complete and continue on the top. So that will mark the attendance. Okay. Some sessions I'll be using the recorded video streaming if I'm not able to present it on live or to enhance the learning experience. And please do submit your mindset activity on the Facebook group. Okay, so this program is for you. So please do submit the assignments and self-evaluate yourself so that you will become the better version of you in the next 30 days. Okay, let's go for the session. So the materials required for this course is you need an STM32F411 nuclear board, okay, and a logic analyzer for visualizing the UART signals for SPI or I2C signals protocols, to study about the protocols, and an ESP8266 module, and a DHT11 sensor for temperature sensor, and ADXL345 and LED and 330 ohms, okay, and relays and HC05 Bluetooth module. We'll be doing two projects in this course. One is the Bluetooth automation, like Bluetooth based home automation. The other is the IoT projects, which uses temperature sensor, okay, wireless temperature data logging to Google Cloud. Okay, so what are interrupts? So interrupts are a specific feature of a microcontroller that allows them to pause the execution of the current program, and it executes a special routine called interrupt service routine, or it executes a special function called the interrupt service routine. Okay, so whenever an event occurs, it passes the current execution program, and it gives attention to the interrupt service routine or the handler, interrupt handler. Okay, so interrupts it will be used for you can use for peripherals GPIOs. You can configure any GPIO pins as an interrupt pin. For example, if you have a fire alarm sensor, okay, so whenever you get alarm from the fire alarm, you have to execute the fire alarm interrupt service routine. Okay, so in that case, the process stops the current execution of the program and gives priority to the fire alarm. So that can be done by using a GPIO pin. And any peripherals, like whenever you receive data or transmit data, like you can generate interrupts, or timer, whenever timer overflows, you can generate interrupts. So coming to the difference between interrupts as polling, interrupts is suitable for real time, whereas polling is not suitable for real time. Like whenever an interrupt event occurs, the interrupt service routine will be called, okay, or it executes the interrupt handler. Whereas in polling, like the processor continuously check for an event. Okay, if that event occurs, it processes the service, it processes the routine, it processes the loop, or for the decision loop. Okay, so that's polling. So when you go for polling, like it consumes a lot of processing power, whereas an interrupt, only when the interrupt occurs, it goes for the interrupt service routine. Okay, so it is suitable for real time, but when you use polling, it is not suitable for real time. Okay, so this is a small example program for the interrupts as well as for the polling. Like whereas the polling, like it continuously check for the condition whether the switch is on. If the switch is on, then it processes the function called get data. Okay, whereas for interrupt service routing, like it will be a loop. It will be it could be of any loop, or you can execute any statements. So whenever an interrupt occurs, like it passes the current execution of the program and goes for the interrupt service routine. Okay, so that's what happens in interrupt. Whereas in polling, like you have to poll for each for every time to check whether the event occurs. If the event occurs, then it processes the data. So it takes more processing power, whereas and it's not suitable for real time. Okay, whereas interrupts, it's suitable for real time. You can have priority kind of thing. So interrupt service routing, these are the functions which is executed when an interrupt occurs. Okay, it is called interrupt service routine or interrupt handler. Okay, so all this interrupt service routine on the interrupt handler will be on the startup files. You will have it on the startup file, which is placed on the vector table. Okay, so which is stored at the starting point of the flash memory. So in ARM Cortex, like in the previous session, we have covered up exceptions and interrupts. We have nearly 15 exceptions, and on the ARM Cortex series can handle up to 240 interrupts. Okay, but in STM32F411 series, like we have around 82 interrupts and 15 system exceptions. So there are two modes available on the ARM Cortex M4 series. One is the thread mode, which is the normal execution mode. The other is the handler mode. So whenever an exception occurs or an interrupt occurs, okay, so the processor is shifts the mode from thread mode to the handler mode. Okay, so when the interrupt finished, then it comes back to the thread mode again. Okay, so the exception behavior, like usually what happens in the exception behavior or the interrupt is you have a main program which is executed. So whenever an exception or interrupt occurs, it puts the current execution program on hold. Okay, and it push the values to stack, and then it fetches the vector address, and it fetches the interrupt handler based on the interrupts. Okay, and it executes the handler. It means the service routine, interrupt service routine or exception service routine. Okay, so this is what happens on exception behavior or interrupt. So coming to the NVIC, so in ARM Cortex M4 series, these interrupts are managed by a controller on the ARM Cortex processor core. So it is on the processor core. Like usually, what happens, the peripherals will be on the supplier side, like the manufacturer side. Texas Instruments or ST Microelectronics will be responsible for the peripherals. So if you want to go through the registers will be available with the ST Microelectronics data sheets. Whereas for the processor core, the registers will be available on the ARM company. Okay, so you have to download the ARM Cortex M4 reference manual. I have uploaded that in the Facebook group. So the nested vector interrupt controller belongs to the processor core. Okay, so it's a dedicated hardware which is sitting inside the Cortex M4 microcontroller, and it can handle. It is responsible for handling interrupts. Okay, so this controller is responsible for handling interrupts. So the ARM Cortex M4 series, like it can handle up to 240 interrupts, and it is called nested because even if multiple interrupt occurs based on the priority, it preempts the lower priority and it gives service to the higher priority. Okay. So that's the reason it's called nested. You can have an interrupt inside an interrupt. Okay, so based on the priority, it will give service. Okay, so there are a lot of NVIC registers where you can set or enable, or you can disable the register. You can disable the interrupts, and you also have pending. You also have pending registers. Okay, so NVIC you have enable registers, disable registers, clear, as well as pending registers. Okay, where you can set the priority, and you can enable the interrupts. Or you can disable the interrupts, or you can pend the interrupts. Okay, you can put the interrupts in the pending state. So these can be done on the NVIC registers. Okay. So this is a block diagram of nested vector interrupt controller. So you can see like the GPIOs are red color, which is connected to EXTI controller. So the EXTI controller is on the peripheral side, which is from the supplier, from the manufacturer, from the ST Microelectronics. So you have to go through the EXTI registers. So the peripherals like CSS, the clock security system, is connected to the non-maskable interrupts, and the peripherals like UART peripheral or timer peripheral or SPI or connected to IRQ. Okay, interrupt request. So every peripheral will have an interrupt request number. Okay, interrupt. I will show you that on the vector table. Like so, NVIC is connected to the processor code, and you also have system exceptions here. Okay, so system exceptions and this stick timer, or these are called internal exceptions or internal exceptions, which is triggered by the processor core itself, whereas the external interrupts are triggered by the environment. Okay, it may be due to the environment, like it can be generated from the GPIOs or UART or the fire alarm. Okay, so the external events will trigger. So there are two types of interrupts. One is the external and the other is the internal. Okay, so the internal events are called exceptions, system exceptions. So there are 15 system exceptions in ARM Cortex-M4 series. Whenever an exception occurs, it goes for the exception handler. Okay, so this is the block diagram. So for GPIO, it has to go via an EXTI controller, whereas for peripherals, it's directly connected to the IRQ. Okay, so the NVIC registers, you have the interrupt set enable ISER registers, interrupt set enable registers, and interrupt clear enable registers, interrupt set pending registers, interrupt clear pending registers, interrupt active and interrupt priority registers. Okay, and software trigger interrupt registers. So these are the registers which is available on NVIC. We'll be using interrupt set enable registers, and if you want to configure the priority, you can use the interrupt priority registers. If you want to set pending interrupt, then you can use interrupt set pending registers or interrupt clear pending registers. Okay, so interrupt set enable registers. So every interrupt set enable registers has 32 bits. Okay, so if it is 1, it is enable interrupt. If it is 0, it is disable interrupt. Okay, so this has to be so totally we have 8 from 0 to 7, ISCR 0 to ISCR 7. I will show that in the STM32. Okay, I just go for Windows show view SFRs. Okay, so these are the Cortex-M4 series, like Cortex-M4 series, like the Cortex-M4. This belongs to Cortex-M4 and this belongs to STM32 F411. Okay, so STM32 is ST Microelectronics F411 processor, and these belong to Cortex-M4 ARM company. So it has been separated. So if you just click the NVIC here, nested vector interrupt controller. So we have ISCR 0 interrupt set enable registers, ISCR 0 to ISCR 7. Okay, so ISCR 0, there are totally 32 bits are there. Okay, 32 bits. So you can so for example, on the vector table, like let me open the vector table. Just give me a moment. Let me open the vector table. Okay, so if you check out this vector table, you have a position here. Okay, this is IRQ position like 0, 1, 2, 3. So it goes up to 82. Sorry, 81. Okay, so 82, totally 82. And these are the like settable. You can configure, but by default it can use up to 240. Okay, so but in F411 series, like you have only 82. So if it is 38, if user 2 is 38, okay, user 2 is 38, then you have to choose the register is 38. The first 32 is ISCR 0. Okay, ISCR 0. You have to configure this. If it is then for 38, it's from 0 to 31, it is ISCR 0. From 32 to 32 to 64, like it is ISCR 1. Okay, so you have to set based on this, you have to set the registers here. Okay, I'll show that in the program, so it will be clear for you. Okay, and you have interrupt clear enable registers and interrupt set pending registers, clear pending registers, active bit. Okay, and external interrupts, it starts from EXTI 0 to EXTI 15. Okay, we have port PA0, PB0, PC0, PT0, like P. So all PA0s, P0 pin is connected to EXTI 0. Okay, if it is P1, it is connected to EXTI 1. You have up to EXTI 15. Okay, from 0 to 15, so totally 16 pins. Okay, so you can use any one of this, like for interrupts like PA0 or PB0 or PC0. It has to be triggered via only the CXTA0. Okay, if it is P10, port 8 pin 10, then it has to be via an EXTA10. Okay, EXTA50. So like this. Okay, you can configure the rising edge you want to trigger when rising edge happens or falling edge, okay, or both. You can configure that on the registers. Okay, so these will be very clear, like once we go through the program, like how EXTA works and how this NVIC register works. Okay, don't worry. And coming to the exception life cycle. Okay, so yeah, exception life cycle, like whenever an exception or interrupt occurs, like the current interrupts, okay, will be processed. If the priority is high, it will be processed. So simultaneously, when this star denotes when the next interrupt occurs. When the next interrupt occurs, it will be on the pending states. Okay, provided the priority is lower than the A. Okay, so if once the service routine is completed, then like the processor gives attention to the B task, like it executes the interrupt service routine of B. Okay, so and once the B completed, then it returns back to the main program. So this is what happens. So when you have like whenever you have a higher priority, then the higher priority like it preempts the lower priority. Okay, for example, so when task A is higher priority, okay, so A is higher priority and it executes and executes. Suddenly we got the interrupt from B, so it puts that in pending states. Once the service routine is completed, it starts again. Okay, when it starts the B task, and again suddenly, like when we get interrupt in A again, like because A is a higher priority, it preempts the B. Okay, it means it holds the B, it holds a service routine of B, and it gives priority to the A. Okay, and it executes A. Once the service routine of A is completed, then it goes back to B and completes the B. Okay, so this green color denotes all these are active interrupts. Okay, and B like inactive interrupts and pending interrupts. So these are the various stages of interrupts. Okay, and interrupt can be active or inactive, or it can be disabled. Okay, or it can be pending. Okay, so preemption. The preemption is nothing but like whenever a higher priority occurs, the lower priority is preempted and it gives service to the higher priority. So that's called preemption. Okay, so I'll just repeat the same thing here. Like you have IRQ1, IRQ2, and IRQ3. Okay, so so the first is IRQ2, like it executes the ISR2. Okay, suddenly an IRQ3 occurs. Okay, and IRQ1 is also occurred. Okay, so IRQ1 is the highest priority. Okay, so IRQ1 is the highest priority. The next is IRQ2, and next is IRQ3. Okay, so what happens is like it gives service to IRQ1. Okay, it means it gives service to ISR1. IRQ calls ISR1, interrupt service routine 1. Once ISR1 is completed, then it gives like it was preempted. Okay, IRQ2 is preempted because since IRQ1 is higher priority, IRQ2 is preempted, so it continues ISR2 back again. Okay, once ISR2 is completed, then it gives service to ISR3. Okay, then it comes to the main task. So this is called preemption. Okay, so whenever a higher priority occurs, the lower priority service routine will be preempted and gives service to the higher priority. So I just repeat the example again. Like we have three levels of priority. One is IRQ1, which is the highest priority, and IRQ2 is the lowest priority, lower than the IRQ1 but higher than the IRQ3. Okay, so IRQ3 is the very lowest priority. So when IRQ2 is arrived, it serves ISR2, interrupt service routine 2. Okay, so suddenly like you got two interrupts simultaneously. One is from the IRQ1 and IRQ3. IRQ3 is the lowest priority, so it gives priority to IRQ1. Is a very highest priority than IRQ2. So what happens? It preempts IRQ2. It holds IRQ2 and it services ISR1. Okay, it services ISR1. Once ISR1 is completed, then it comes back to ISR2 and it executes that. Once ISR2 is completed, then it executes the ISR3. Okay, so this is called preemption. Okay, So tail chaining, what is tail chaining? Okay. So the tail chaining, so whenever an interrupt occurs, okay, it goes to the interrupt service routine, and suddenly another interrupt occurs. Instead of returning to the main program, like once the service is completed, it executes the next interrupt. Okay, without returning to the main program. Without returning to the main program, it executes the next interrupts. Okay, so all the interrupts, it executes all the pending interrupts are executed. Once all the pending interrupts are executed, then it goes to the main program. So this is called tail chaining. Okay, so here the foreground is the main program. Okay, so you have a push. So whenever an interrupt occurs, when IRQ1 occurs, a push is occurred, like stacking is happen. Okay, through push, and it services ISR1. Okay, once ISR1 is completed, we also have IRQ2 now. So it goes for tail chaining. Okay, instead of popping up, instead of unstacking, it goes for tail chaining, and it executes the ISR2. Okay, it executes the interrupt service routine 2, and then it finally, once the interrupt service 2 is completed, and then it goes for unstacking, like it pop-ups. Okay, pop is for unstacking, and finally it returns to the main task. So this is called tail chaining. Okay, so these are all the interview questions, like what is tail chaining, what is preemption, and what is interrupt, what is NVAC. So you can get thorough on this topic. Okay, so let's go for the GPIO interrupts. Let me open up the STM32. Okay. So first I will explain you the concept. What we are going to do is, like, we have a nuclear board with us. So a nuclear board, we have only one push button, which is called B1, which is connected to PC13. Okay, port C13. You can get this schematics from nuclear schematics from page 2. So this push button is connected to PC13. Okay, PC13, like it's active low. So whenever you press, it will be low. Okay. So the external interrupt controller block diagram. This is the external interrupt event controller block diagram. Like you can get this from page number 256. Okay. So 258 reference manual, like where for PC13, like we need VXTA13. Okay, PC13, because if it is PC0, then we have to take EXTA0. PC1 is EXTA1. So for us, it's EXTA13. Okay, PC13 is EXTA13. So these are like GPIO open is connected to the EXTA, where you can enable this interrupt on this EXTA pins. Okay, and it is fed to the NVIC, nested vector interrupt controller, and it goes to the processor core. Okay, so you can enable and disable the IRQ on this NVIC registers. You can also enable and disable the interrupt delivery to the processor on the EXTA. So for EXTA, you can check out the EXTA registers. Let me show that. Okay, so you just go for the STM32. So these are all NVIC registers. Okay, whereas for EXTA, you can go from this STM32 these are all EXTA registers. Okay, EXTA register, like rising edge, falling edge, can be configured by using these registers, and pending register can be configured here. Okay, the other important register is system config. System config. Okay, where you can config this EXTA CR1 control registers, EXTA control register 1, 2, 3, 4. Okay, so these are the 3 registers which are important. Okay, let's create a new project. So we are going to whenever we press the push button on the nuclear board, it has to go for the interrupt. Okay, interrupt service routing. So that's the program which we are going to do today. Okay, I will just go for file, go for new, just create a STM32 project. File, go for new, create an STM32 project. Choose board selector. Okay, just type Nucleo F411RE. Choose this. Click next. And here you have to type, just give a file name like interrupt GPIO demo. Okay. Click empty, click finish. Okay, I just click the source file, go for main program. Okay, I just remove all these files. Okay, so first we have to just open the data sheet. Let me go for the block diagram. Okay, so we have to use GPIO C here. Okay, GPIO port C, so which is connected to AHB1 bus. Okay, the other is EXTI T, which is connected to ABP2 bus. Okay, we need EXTI for the external interrupts, and we need GPIO C, port C, which is so AHB1 ENR, and we also need APP2 ENR. Okay, so let us just go for the reset clock control. Okay, so AHB1 ENR. Okay, this is the value for AHB1 ENR. So I just unt 32 underscore T. Okay, AHB1 ENR. Okay, you just typecast this. Okay, so copy this, and this is APP2 ENR. Okay, the next is we need GPIOC. GPIOC. Okay, okay, GPIOC. Okay, and just go for EXTI. Okay, so EXTI pending register. This is a mask register. Okay, falling edge, to configure the falling edge, FTSR. Okay, and sysconfig, just go for sysconfig. Okay, so you have to take the CR4. I'll tell you why CR4. You just go for this EXTI. Okay, okay, so you have EXTI FTSR, EXTI for. sorry, sysconfig here, system configuration registers. Okay, this is EXTI-CR1 control register 1. Okay, we have EXTI-0, 1, 2, 3. Okay, in CR2 we have 4, 5, 6, 7. We need 13. Okay, for 3 we need 8, 9, 10, 11. Okay, we need EXTI-13. So EXTI-13 comes under sysconfig EXTI-CR4. Okay, so we need this register. So you just copy this, and I'll just okay. So this is the address. So I just copy this address and I change this one. Okay. The next is NVIC. We need NVIC next vector ISCR1. Okay. Because it is we need ISCR1 because like you just go for the vector table. Okay, let me open the vector table. Interrupts, interrupt. Okay, so if you go to the vector table, and if you found out EXTI-15, EXTI-13, EXTI-13. Okay, so EXTI-13 is comes under here. Okay, from 10 to 15. EXTI line from 10 to 15 interrupts, it's 40. Okay, the IRQ number is 40 here. The position is 40. Okay, this is the position. So the position for this EXTI line interrupt is 40 here. Okay, this 47 is the priority. The next is the priority. So 40 is the position. Okay, so 40 is the position. So for ISCR 0, we have only 32, 0 to 32. So only from ISCR 1 is we have 40. Okay. Yes, we have 40. Okay, so we need to set. So this is 32, 33, 34, 35, 36, 37, 38, 39, 40. You have to set this bit. Okay, you have to, so we have to take NVIC ISCR1. Okay. Okay. Copy this address. So this is to enable the AHB1 bus, AHB1 bus for GPIO. Okay, this is APP2. Enable APP2 bus. Okay, for EXT for EXTI. Okay, this is to enable GPIO EXTI pending registers. Okay, now let us write a program called void button init. Okay, button underscore init initialization. Okay, so first let us configure this one. How to configure GPIO-C. Okay, just go for this reference manual, RCC register. Just click reset clock control. Okay, and you just go for RCC registers, AHB1 ENR, peripheral enable registers. Okay, this AHB1 ENR. Okay. So we have to set GPIO-C here. Okay, this is 0, 1, 2. Okay, this is 2. The position here is 2. So you need to R 1, okay, U for unsigned, and this is to shift it for 2 times, okay. And next is APP2ENR. That this, so if for APP2ENR, you just go for APP2ENR. Okay, this is APP1, this is APP2. You have to check for the system config, okay, sysconfig. So APP2ENR, here it is, sysconfig is here. System configuration controller clock enable, okay. System configuration, so you have to enable this APP2ENR. Okay, it's 14, so let me shift that to 14. Okay, the next is just go for this system configuration. Once you enable system configuration, just go for the system configuration, sysconfig, registers. Okay, ours is EXTI CR4. So it is 13. Okay, so we have to enable this one, 13. If it is, we are using port C. So for port C, you have to set 0010. Okay, you have to set 0010. So 1 is 5. Okay, by default, the reset value is 00. Everything will be on reset, everything will be 00. Okay, so we have to set 1 at 5th location. Okay, because 0010. That's a code for 0010 is a code for port C. So our pin is PC13. Okay, so we have to put PC for PC. If it is port A, we have to put all 0. Port B 0001. Okay, so 0010 we have to set. So this is the 5th pin we need to set here. Okay, so copy this. This is the 5th pin. You need to shift the 5th pin. Okay. So next is to configure the let us configure the falling edge. Okay, just go for the EXTI FTSR. Okay, falling edge for the 13th pin. So 13th pin is here. So 13th. Okay. So to configure, if you put 1 at this place, it is falling trigger enabled. Okay, so falling edge is enabled. So ours is PC13. So PC13 is 13th pin is here. Okay, so 13th pin is here. So you need to enable this 13. So you just copy this and put 13 here. Okay. Next is you have to enable the ISCR1. ISCR1 is 8. Okay. I'll tell you how it is. Like this is so 0 to 31. Okay, it is 0 to 31. So this is 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay, 40. So if you start from 0, 1, 2, 3, 4, 5, 6, 7, this is 8. Okay, so we have used 8 here. Else you can put modulo of 32. Okay, so we have set this one. Okay, let's call the main program. You call this button in it. Okay, and just put a simple while loop. Okay, So now we have to configure the interrupt handler. Interrupt handler for that would be for, it would be on startup file. You just go for the startup file. You check for exti 15. So exti 4 is there. Exti 15. Okay. exti 10 to 15. It will be of exti 9 to 5 is here. Here it is. Okay. Copy this. So that's the handler, interrupt handler. Okay, you can put void. So this is the handler, like void. Okay. So I just put printf. Button is pressed. Okay. So if you button is pressed, right click, build the project. Okay. Right click, go for debug as STM32 application. Go for the debugger, choose ST-Link, enable, click apply, click OK. Okay. Switch. Okay. So I just run the program. Okay. I'm going to press the button here. Like I have a breakpoint here. I'm going to press the button now. Okay. So okay. So it is not enabled now. It is not coming to the interrupt service routing. Okay, let's clear this pending register. Okay, just terminate and relaunch. Click switch. Okay, so I just remove this breakpoint. Right click, toggle breakpoint. Sorry, right click. I'll just remove the breakpoint. I remove all the breakpoints. Okay, I just keep one breakpoint at here. Okay, hit the run button. Like currently, it is not in the interrupt service routing. Let me push the switch now. Okay, I think there is something problem. Like let us debug the code. Okay. So let me check the SFRs. Just go for the SFR. First, we'll go for AHB1ENR. Okay, AHB1ENR on the RCC register. AHB1ENR is AHB1ENR. Okay, AHB1ENR is not set. Okay, let me terminate and relaunch the program. Click switch. I just go step by step execution now. Okay, so it has to set AHB1 ENR now. Okay, CEN is set now. Okay, let's check APP2 ENR. It has to set the APP2 ENR now. So APP2 ENR. Okay, here sysconf it's set. Okay, so we have to set the sysconfig ext4. So 13 has to be set now. Okay, so 13 has been set now. So 0010. Okay, it's configured correct. So NVIC ISCR1. Let's check this. Go step by step execution. Okay, so I just execute. So you have to it has to be NVIC ISCR1. Okay, it is set here. Okay, so everything is perfect. So it comes to the button unit. Okay, so it hangs the program here. So if the button is pressed, it has to be come here. Okay, we change this to volatile. Okay, let me check now. The problem is we cannot set the mask register. Let me configure the mask register. Okay. Let me build the project again and right click and debug the project. So when you press this button, like it should come to this IRQ handler. Okay. So let me remove the breakpoints. Okay, I just hit the run button. Okay, so it's in while loop now. So when I push this push button, like you can see this it jumps to the printf statement, okay, and it executes this line. Okay, so this is an example for the interrupt using GPIOs. I just explain the code again. You just configure the ENR, AHB1 ENR, and like APP to ENR, which is enable the GPIO clock access for the GPIO, enable the clock access for the EXTI, GPIO C, and pending register EXTI, pending registers, mask registers, and FTSR, falling edge. Okay, so you have to configure the falling edge, and this config like 40013814. We have configured for falling edge because it's the switch what we have is pulled down. Okay, and system configuration registers EXT CR4, you have to choose EXT CR4 and NVAC ISCR1. Okay, so enable this GPIO C and enable the sysconfig here and sysconfig EXT13 line here, and falling edge and EXTI mask register and ISCR. Set this bit and call this button in it. Okay, so it will be in loop. So whenever you press the switch, it comes to the handler. So this handler has to be copied from the startup file. Okay, let's go for the UART demo. I'm going to copy the same program which we done on the previous class. Like I just copy the project. Okay, right click copy and right click paste. Okay. So I just give UART receive interrupt demo. Okay, so I just give the name UART receive interrupt demo. Click the source file, click main.c. Okay, so this is the program which we have configured on the day. So you have to modify only two. You have to modify only at. You have to set the control register. Okay, just go for the data sheet. Go for the user data sheet. Okay, user register, like click user registers. Okay, go for the CR1 registers. CR1. Okay, so user CR1, like you have to set this RxNEIE. Okay, the fifth bit. So RxNEIE is interrupt enable. Okay, you can also set for transmit TXE interrupt enable. So we want to set RxNE interrupt enable. Okay, let's set this. You just copy this. Okay, to set, I'm going to shift 5 times. Okay, so we have set this bit, and you need to add the NVAC ISCR1. Okay, so hash define so from the vector table you sort to IRQ number. Just take the user to IRQ number is 38. Okay, so it has to be taken from the vector table. Like you just go for the vector table, interrupts. Okay, so you just come for user 2, it's 38. The number is 38. Okay, IRQ is 38. You have to take in this value from there. Okay, and you need the window show view SFRs like ISCR. You need the pending register as well as the ISCR register. Okay, ISCR and ICE. So just copy this. It is ISCR1. Okay, ISCR1. So this is the address for IS PR, it's the address is okay. Okay, you have to set. You put this modulo 32. So to set the particular bit, else you need to set it manually. Okay. How to enable ISCR1. And the remaining code, like you can have this code, we can have it. You just go for the startup code, source startup file, and choose the user to handler. Here it is. Okay. Okay, I just copy this code. Paste it here. We clear ISPR pending register. Okay, so whenever you receive the data here, like this code will execute. So let me try this one. Right click, build the project, go for debug as STM32 application. Okay, click OK. Choose this debugger ST-Link and also choose serial wire viewer. Okay, serial wire viewer enable. Click apply, click OK. Click switch. So I just hit the run button now. Okay, so just open Arduino IDE. Okay, I just open this Arduino IDE. I just hit the run button and I try to put A here. Okay, okay, so the LED is blinking now. You can see, and B here. Okay, so LED is off and I try to press A. So whenever an interrupt occurs, user interrupt occurs, just come for this interrupt handler. Okay, you can keep a breakpoint and you can check. I just keep a breakpoint and I try to push value through the Arduino IDE. Okay, so it just comes to this interrupt handler, user to interrupt handler. Okay, and it just started executing this code. Okay, so this is an example for user to interrupt. So with this I end the session. So it's very simple. I just give a recap. You just copy the previous program. Okay, you just configure only the CR1 register, control 1 registers where you have to enable the interrupt. Okay, after that configure NVIC ISCR1. Okay, this modulo 32 is nothing but This is 38. Okay, this is 38. It means you have to set the you have to set on the SFRs in the ISCR one. Okay, ISCR one, because this is 32. If 32, this is, you have to set this bit. Okay, in the previous case it is 40, so we set this bit. It is 38 here, so we set this bit here. Okay, or you can directly put 0, 1, 2, 3, 4, 5, 6. It's 7. Okay, sorry, 6. 6. You can directly put 6 here, or you put modulo of 32. Okay, so this will give you the ISCR register, and you just copy the user handler, user2 handler, and put the code here. Okay, so with this I end this lecture today. So let's go for the okay, let's go for the mindset lesson. So we have caught up the GPIO EXTI13. We have caught up this code, this code, and we also covered up the user2, which is connected to IRQ number 38. With this, I close the session. So thank you so much for your time. So today mindset lesson is about respect your own decisions and practice it daily. Okay, so for example, if you want to wake up at 4:30, and if you try to snooze the alarm, it means like you are giving up. Okay, so it tells your brain, you subconsciously told it gives information to the brain like you are not the person who is consistent. Okay, so you will give up easily. So practice each and every decision which you take, and respect every decision which you take, and practice it daily, and be consistent on your decision, and practice the art of never giving up, even on very simple things. Okay, so because that will develop the habit of giving up. Okay, so just even if it is a simple wake up which you get up early in the morning, never give up on the morning. Okay, the moment you give up in the morning, like it tells you the subconscious mind that you are the person who give up easily. Okay, so, and the fourth point is love yourself. Okay, so these are the lessons which I like to share you today. So please do practice the activity, mindset activity, like write down your top 10 goals, and write down your top 10 ideas to achieve your goals, and 30 minutes of workout, and 15 minutes to meditate, and 10 minutes to visualize already achieve the goal, and 10 minutes to focus on the day plan, and 2 hours of learning. Okay, and please do post it on the Facebook group. So thank you so much for your time, and see you in the next session tomorrow. Until then, bye bye, take care. Thank you.